Hey everybody, this is Larry. This is me doing an extra bonus to having a temp problem, an RNG. So let's go. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this one, especially since the other actual daily problem is what is it, power of 2? I don't even remember already. That was like, so let's get something slightly more challenging, and we have a medium problem. Someone called 911 because it's an online election. A lot of downloads, but we'll see. All right, so you're given two integer arrays, persons, and times in the election I vote was cast for person I at times I. Okay. For each query at a time I, find the person that was leading the vote. Okay, I mean, it's kind of unnecessary and weird. That's not how democracy works, but I guess that's kind of okay. Yeah, there's only one time where it matters, which is at the end when everyone casts their votes, of course. But anyway, all right. Uh, Alright, for each query T, find the person that was leading the election at time T, vote casted at time T counts. Okay, in case of a tie, the most recent vote wins. Okay. So basically you have and you have times. Okay, so this is a little bit awkward because you are given these things. And I say awkward only because like I feel like if you were trying to pretend this is a real world thing, then of course you would say like you could like there's another function maybe you could cast a vote at a certain time and then you can't do that in order or something like that, but here you can actually what they want you to do I suppose is pre-process the times, so that when you do a query you can just do like some sort of binary search type thing. I mean that okay, but yeah, how many candidates are there? I guess it could be. I mean, there are only 5,000 people, or like 5,000 votes, so it can be. Yeah, so up to 5,000. Hmm. How do I want to do it? I mean, if there were not that many candidates, then then what you can do is just do like a prefix sum or prefix array type thing, right? But it is a little bit awkward for sure. Because then it takes 5,000 or like a loop of 5,000 every time, which is a little bit awkward. Is that fast enough though? At most 10,000 or 10 to the fourth times 1,000 is already going to be 10 to the 7, right? So yeah, so that maybe that's a little bit too expensive. So we have to do a little bit smaller than that, right? How do we want to think about it? I mean, the times part doesn't really interest me that much. We could either do a binary search or you could normalize all the numbers. It's really not a big deal. But I mean, it's probably still gonna be prefix sum. I mean, okay, so it could be prefix. Initially, my idea was gonna be prefix sum, but and then you kind of just do it that way. But I guess what you can do is just calculate the winner at every time, or there are only 5,000 votes, so you can just calculate the winner of 5,000 votes, or like 5,000 distinct times. Less than that actually, because in theory sometimes they vote together. But oh wait, it's actually strictly increasing order. Okay, well fine. But either way, what I mean is that yeah. If this is already in strictly increasing order, that's even easier. But yeah, we'll just kind of keep track of who's winning, and then at thing we just let the viewer know, right? So how and the winner is, it doesn't have to be majority, right? It's just leading. Yeah, okay. So I was going to use what was it, Baltimore or one of those? I forget. Is it Baltimore? The voting algo, but the majority algo. But I guess now I cannot. Okay. So I mean, okay, there are a couple of ways we can think about this, and all of them, yeah. I mean, I think my hesitancy is just about using too many data structures, but maybe it is necessary, and if it is necessary, it is necessary. So basically, the idea that I have now is just bookkeeping from what we said. So basically, we keep track of all the winners of all the possible times, so that when you get the T later, you just kind of binary search. So from that, and keeping in mind they only have 5,000 things, so we can probably just keep two things, right? a sorted list, which you can maybe think about as a heap that you can dynamically look at, or the other, because in that case, I think technically, if you're really careful and you have a real max heap that you can update on, then this is actually the ideal case for it. But we'll just use sorted list as a proxy for that, right? And then just the current votes, and then yeah, that's pretty much it, right? So okay, so then here we have maybe votes is equal to collections.counter. That's just like a frequency thing, maps a person to votes. Pretty straightforward. And then sorted list for so this thing is so that we can get the most vote, the person with the most vote at any time. So we could do that in, I guess, I don't know if get max is over 1 or over log n, but either way it's relatively cheaper, right? So yeah, and then maybe we have like winner by time or something like that. And then that'll be our array that we just kind of, yeah. And then here, then now we can just do for person time in zip person's times, right? And then now, so votes sub person we increment by 1, right? Yeah. So then maybe we can do if person not in vote, then we have to set it up is equal to 0. Even though, I mean, I know that is a default thing, so you don't actually need to set it up manually, but it also allows us to do the sorted list, which we need to name a little bit better, but whatever. It's the same way that like a heap, you just name it a heap maybe. But yeah, dot add 0 person, right? So that's just basically the thing, and then now you increment it. But here now you can say sl dot remove votes to a person. Person. I know that this this looks a little bit awkward, but just so that we don't have to check for it. And then we increment by 1, and then we can add back the incremented thing, right? Oh, I guess this is now updated, so yeah. And that's pretty much the idea. And then winner by time, we can now update time, and then the SL, I guess we always have a thing, right? So SL of the last element, just the person, right? So yeah, oops, yeah, because basically we're getting this index on the last one, which is SL max, and that's pretty much the idea. We'll just print it out here for now, just for funsies, and then we can kind of just debug it real quickly. Or like, I just like to get a visualization. And yeah, and I visualized type having a typo apparently. So yeah, you could see that at time 0, 0 is winning, then 5 is 1. Oh, we have to. What about in case the tie, the most recent vote? Huh. We actually have to fix that then. That's annoying actually. I mean, it's not okay. I mean, I think our idea is about 95% done. You kind of see what we're doing here. You could kind of, at time 5, 1 is winning, time 10. But of course, we have to kind of do this other tie breaking thing, which is annoying. But again, it's just bookkeeping, and by that I mean we just have to keep track of it, right? So last time is equal to or just a lookup table, right? So then here we can say last time of person is equal to -1, and here we just add an additional tiebreaker because we want max. So then here we can say last time person, which is -1. I guess you want to just for symmetry, then we could write something like this, and then yeah, now we remove that back. We increment, we set last time a person is equal to time, and then we just update it back. This is what the way of updating. The way to update these is just remove and then add, right? And we just have to make sure that we're consistent. And then yeah, and then now we don't have to change that, and we should be good. I actually don't know what to expect. Ooh, oh yeah, we have to change this because now it is on index 2. Oops. This is why you use like a name tuple or something like this is where so you don't make these kind of silly mistakes. But okay, yeah. So then now 5 and then 10 and then 15 and then I don't know if this is right, but it doesn't even matter, right? Because it just we just we just need it. And then now I mean I guess it matters in the sense that you really want to deliver it, but for now we'll spend the time by writing the queue, right? So now we can do a binary search, right, on the winner by time. Oh, I guess I need to make this part of self. Whoops. So here we have winner by time. We want to do binary search. What is bisect left? Yeah, we want to be bisect. Wait, let me double think. Basically, this is the time it is updated. So if at a given time, actually it's not bisect. So actually it's bisect right, but then we have to subtract one because you basically and I'm just thinking it through right now, but the idea is that okay, let's say you have 10 and 20 in your array somewhere as your searching thing. If you have 15, you actually want to get 10, right? Because we haven't done the votes for 20 yet, so we want to get 10. And of course, if this is 10, then we do also want to get 10. So that means that we want to bisect right to the next thing, and then we subtract 1. So okay. Yeah. T negative. No, this is should be infinity. So whatever. You want this to be infinity so that if the time is exactly the same, you skip to the next one. So then now you have index is equal to this, and then now if index minus 1 is between 0 and length of and this should always be true. I don't know how this can be false, so that would be amusing maybe. So maybe we can assert this because I don't know what to do with. I mean, it could be false if you do it before the first element, but I don't. I mean, I just assume that it'll be well formed, but I don't actually. It doesn't. Maybe it's like stated in here somewhere like this thing, but okay, fine. So I think this is fine, but then now we can return self.winner by time, index minus 1, and then the second element, which is 1, right? Yeah. All right, let's give it submit. Hopefully I didn't make a silly mistake. And yep, there we go. What's the complexity here, right? It's just a lot of pre-processing. This is obviously going to be O of log n, right? I mean, this is a binary search. This has almost n things because for each of the inputs, we have each of one item here. So it's going to be a linear time, or linear space, sorry. Right, and yeah, this is going to be O of log n. So yeah, so all of these three things have O of n space, so it's going to be O of n space, and this as well, of course. For here, I mean, for each of the n items, the loop goes n times. We do a couple of log n operations, the sorted list mostly. Everything else is O of 1 probably. And so yeah, so that means that this is going to be n log n as part of the pre-processing. And that's pretty much all we have for this one. Let me know what you think. We got it in 31 lines of code. And yeah, that's it. Stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye bye.